All right, let's go.
Number 8. The original crime. Hawking accuses the universe of breaking its own rule. In 1976, Stephen Hawking published a calculation that made the rest of physics deeply uncomfortable, and it has stayed uncomfortable for 50 years. Quantum mechanics has one rule it is never allowed to break. It is called unitarity. In plain terms, it means information cannot simply vanish from the universe. If you burn a book, the ash, the smoke, and the heat technically still contain every bit of information about that book, scrambled by recognition but never actually destroyed. In principle, a being with perfect knowledge of every particle could run the process backward and reconstruct the book. Nothing is ever truly gone, just badly hidden. Hawking's calculation said black holes do not follow that rule. He showed that black holes are not perfectly black. They slowly radiate energy away through a process now called Hawking radiation, and over unimaginable timescales, this causes them to shrink and eventually evaporate completely. That part was already a triumph, but when Hawking worked out the details of that radiation, he found it was thermal, random. It carried no imprint of whatever had fallen into the black hole to create it. Drop a star into a black hole. Drop an encyclopedia into the same black hole. Wait for both to evaporate. According to Hawking's original math, the radiation coming out looks identical either way. Not similar, identical. Every detail about what fell in is gone, not scrambled, not hidden, actually erased from existence when the black hole finally disappears. That is the crime. Quantum mechanics says information cannot be destroyed. Hawking's own equations, applied to his own discovery, said black holes destroy it anyway. Two of the most trusted theories in all of physics were now openly contradicting each other, and somebody had to be wrong. Number 7. The Firewall Paradox, the solution that created a wall of fire at the edge of reality. For decades, physicists tried to patch the paradox without confronting it fully. Then, in 2012, 4 researchers, Ahmed Almheri, Donald Merolf, Joseph Polchinski, and James Sully, showed that patching it quietly was no longer an option. Their argument, now called the Firewall Paradox, works like this. If information really does escape a black hole hidden in the Hawking radiation, then very late in the black hole's evaporation, that outgoing radiation must be entangled with radiation that already left earlier. But standard quantum mechanics only allows a particle to be maximally entangled with one other system at a time. The outgoing radiation is also supposed to be entangled with whatever is still inside the black hole, because that is what keeps the passage through the event horizon smooth and uneventful for anyone falling in. You cannot have both. Either the entanglement with the interior breaks, or the entanglement needed to preserve information breaks. Something has to give. If the entanglement with the interior is the one that breaks, the smooth, gentle event horizon that general relativity promises does not exist anymore. In its place is a wall of extremely high energy radiation sitting right at the boundary, an actual firewall that would incinerate anything falling through instantly rather than the graceful, unremarkable crossing physicists had always assumed. This was not a fringe objection. It was published by serious researchers using the same tools that built the paradox in the first place, and it forced the field to admit that saving information might come at the cost of destroying one of general relativity's most basic promises, that falling through an event horizon should feel like nothing special at all. Number 6. The Page Curve, a graph that physicists trusted more than their own intuition. In 1993, physicist Don Page made an argument that reframed the entire problem using nothing but the mathematics of entanglement entropy. If a black hole is truly evaporating in a way that preserves information, Page showed there is a very specific pattern the entanglement between the black hole and its radiation has to follow over time. Early on, entanglement should rise, exactly as Hawking's calculation predicted. But if information genuinely survives, that entanglement cannot keep climbing forever. At some point, roughly the halfway mark of the black hole's evaporation, it has to turn around and decrease eventually, returning to zero once the black hole is completely gone. This turning point became known as the Page curve, and for a long time it was a prediction with no matching calculation behind it. Hawking's original method only ever produced the rising half. Nobody had a way to actually calculate the turnaround using the tools available at the time. Then, in 2019 and 2020, two independent research groups found a way to compute it directly using a technique from quantum gravity called replica wormholes, treating spacetime itself as though it could branch and rejoin in extra copies during the calculation. When they ran the numbers, the entropy curve did exactly what Page said it should. It rose, peaked, and came back down. For the first time, a calculation grounded in gravity itself, not just an abstract argument about what quantum mechanics ought to require, produced the shape needed for information to survive. It did not explain how the information gets out. It just proved mathematically that it must. Number 5. ER equals EPR. Two different mysteries that might secretly be one mystery. In 2013, Juan Maldacena and Leonard Susskind proposed something that sounds less like physics and more like a magic trick, except the mathematics behind it is entirely serious. ER refers to Einstein-Rosen bridges, the technical name for wormholes, tunnels connecting two distant points in spacetime through the mathematics of general relativity. EPR refers to Einstein-Podolsky-Rosen entanglement, the strange quantum connection between two particles that lets a measurement on one instantly correlate with the other, no matter the distance between them. Maldacena and Susskind's proposal is that these are not two separate phenomena that happen to share an initial. They might be the exact same phenomenon, described in two different mathematical languages. Every pair of entangled particles on this view is connected by an impossibly thin, non-traversable wormhole. Entanglement is not just a strange correlation sitting on top of ordinary spacetime. Entanglement might be what builds spacetime in the first place. Applied to the information paradox, this reframes the whole firewall argument. The outgoing Hawking radiation is entangled with the black hole's interior because it is geometrically connected to it, threaded together by microscopic wormholes rather than sitting in the kind of ordinary entanglement that would force a contradiction. If ER equals EPR is correct, the firewall problem may simply dissolve because the entanglement was never the kind of entanglement the paradox assumed. This idea has become one of the most influential frameworks in modern theoretical physics, feeding directly into the entanglement island calculations that produced the Page curve. It has not been experimentally confirmed, but it has quietly become one of the most productive wrong or right ideas in the field, because even physicists who doubt it admit it keeps generating results that work. Number 4. Black hole remnants. What if evaporation simply stops before the end? One of the oldest proposed solutions is also one of the simplest to state, even though the physics behind it is not simple at all. What if a black hole does not evaporate all the way to nothing? What if, as it shrinks and approaches the smallest possible size physics allows, the Planck scale, the evaporation process halts, leaving behind a tiny, stable remnant that holds on to all the information that ever fell in? This idea resurfaced with real mathematical teeth. In 2026, researchers publishing in General Relativity and Gravitation proposed a specific geometric mechanism for this using a 7-dimensional structure called a G2 manifold, a framework connecting black holes, extra dimensions, and torsion in spacetime itself. Their calculations suggest a remnant with the mass of the Sun could store approximately 1.515 times 10 to the 77th power qubits of information, an amount their analysis found to be exactly sufficient to preserve everything the black hole originally swallowed. If correct, this would mean the information paradox never required rewriting quantum mechanics at all. It would mean the missing information was never actually missing. It was simply locked inside an object too small and too subtle for our current instruments to have ever noticed. The proposal remains one candidate among several, not a confirmed answer, but it represents a real, mathematically worked-out shift in how seriously physicists are willing to take the idea that the answer might be sitting quietly at the smallest possible scale of the universe, still there long after the black hole appears to be gone. Number 3. The black hole to white hole bounce, a black hole that turns itself inside out. A newer and stranger proposal comes from a completely different direction: loop quantum gravity, the framework that treats space-time itself as built from discrete, indivisible units rather than a smooth continuum. In this picture, a black hole does not collapse forever toward an infinitely dense singularity, and it does not simply evaporate away into thermal radiation either. Instead, the extreme density near the center triggers a quantum bounce, the same mechanism some cosmologists use to explain what might have preceded the Big Bang. The collapsing matter reaches a maximum density, refuses to compress any further, and rebounds. The black hole transforms into its mathematical mirror image, a white hole, an object that expels matter instead of consuming it. Under this scenario, nothing was ever destroyed. The information that fell in during the collapse phase gets released again during the bounce, carried out as the black hole transitions into its white hole phase. Depending on the specific version of the model, this transition might happen quickly, appearing to an outside observer as an unusually abrupt end to what looked like a normal evaporating black hole, or it might take a very long time, stretched out by the extreme time dilation near the horizon. This approach sidesteps the firewall argument almost entirely because it never relies on Hawking radiation being the vehicle that carries information out in the first place. The information leaves through the bounce, not through subtle correlations in thermal radiation. It remains a minority position tied closely to the broader loop quantum gravity program, but it offers one of the few resolutions that does not require inventing anything new at the event horizon at all. Number 2. Soft hair and Hawking's own last attempt. Even Hawking eventually changed his mind. For most of his career, Hawking was the paradox's most stubborn defender, insisting information really was lost. In his final years, working with Malcolm Perry and Andrew Strominger, he changed his position. Their proposal involves something called soft hair. For a long time, physicists believed black holes could be fully described using only 3 numbers: mass, electric charge, and spin, a principle sometimes summarized as black holes have no hair, meaning no other distinguishing features survive the collapse. Hawking, Perry, and Strominger argued this was incomplete. Black holes can also carry an enormous number of extremely low-energy quantum imprints called soft photons and soft gravitons sitting on the horizon itself, encoding subtle details about exactly what fell in and how. In one of his final papers, published shortly before his death in 2018, and in follow-up work Hawking co-authored on information preservation, he explored the idea that gravitational collapse might not produce a true horizon at all, only an apparent one, a boundary that looks like a point of no return locally, but does not actually trap information permanently the way a true horizon would. This version is explicitly supported by the ADS-CFT correspondence, and Hawking noted it was the only resolution he could find that remained fully consistent with the deep symmetries physicists believe the universe must obey. The man who discovered the paradox spent his final working years trying to dismantle it and arrived at a version of the answer built on horizons quietly holding far more memory than anyone had ever accounted for. Number 1. Why this argument refuses to end. 50 years later, the field can still not agree, and that might be the point. In November 2025, physicists gathered for a program explicitly titled 50 Years of the Black Hole Information Paradox. 50 years is a long time for a single question to keep an entire field of theoretical physics occupied without a universally accepted answer. Here is where things genuinely stand out of 2026. The page curve calculations from 2019 and 2020 convinced most theoretical physicists that information is preserved, not destroyed, at least within the idealized mathematical models physicists know how to fully solve, models built on a special curved geometry called anti-de Sitter space. That is a real hard-won piece of progress. A majority of the field now treats black hole evaporation as fundamentally unitary, but translating that success from idealized toy universes into the real, flat, expanding space-time we actually live in remains unfinished. Nobody has yet shown with the same mathematical rigor exactly how the information gets out for an actual astrophysical black hole, the kind orbiting real stars in our real galaxy. The remnant theories, the wormhole conjectures, the black-to-white hole bounce, and Hawking's own soft hair proposal are all competing, only partially confirmed attempts to answer that harder, more physical version of the question. This is not a failure of physics. It is what physics looks like while it's actually working on something this deep. Every serious proposed resolution on this list has forced physicists to reconsider what spacetime is actually made of, whether wormholes and entanglement are secretly the same thing, whether horizons are as absolute as general relativity always assumed, and whether black holes might be built from something more like a Planck-scale hard drive than an inescapable void. The paradox began as an argument between two trusted theories. It has become one of the only known experimental adjacent windows into quantum gravity itself, a question small enough to state to a child and unresolved enough to occupy the smartest people alive for half a century. Something fell into every black hole that has ever existed. The universe has not yet told us for certain whether it kept the receipt. 8 theories, a crime discovered by Hawking's own equations, a wall of fire proposed as the price of keeping information alive, a curve that had to rise, peak, and fall to save quantum mechanics, finally calculated using wormholes made of mathematics rather than matter. A conjecture suggesting entanglement and wormholes were secretly one thing all along, a remnant small enough to hide in, holding more information than seems possible for its size. A black hole quietly turning itself inside out into a white hole on the other side of its own collapse. Soft, nearly invisible hair on the horizon, discovered by the same physicist who once insisted none of this needed saving. And a field that 50 years later still has not closed the case. 2 of the most trusted theories in physics disagreed about something as simple as whether the universe forgets. We still do not fully know which one was right. Subscribe to Cosmic Hives. See you in the next one.